I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
Hello, my name is Ben Bussey and I'm the Senior Exploration Scientist in the Lunar Discovery Exploration Program at NASA headquarters. My background is a lunar scientist with my area of expertise is the lunar poles, and today I'm going to be talking to you about the science and exploration value of the lunar poles. The lunar poles, often you can ask the question, are they a good place to go for scientific exploration? And the short answer is yes. The lunar poles are a very special place on the moon and they offer a unique exploration opportunity. A key factor is the fact that the moon's spin axis is only tilted about 1.5 degrees from the ecliptic plane. In comparison, the Earth's spin axis is tilted 23 degrees to the ecliptic plane. And this is why we get 4 seasons. This is why we get weather in summer that's very different to weather in winter. The moon is different, it's only 1.5 degrees. And at midsummer, the center of the sun would only be 1.5 degrees above the horizon. So it doesn't take much topography to have drastic effects on the lighting. If you're at a high point near one of the poles, it's feasible that you can have areas of quasi-permanent sunlight. So these are regions that are lit for the vast majority of the time. Most places on the moon are a typical lunar day, which is 28 Earth days. You have 14 Earth days of sunlight, 14 Earth days of darkness. At the poles, you can have places that are lit constantly for long periods of time. Now these are extremely interesting because first of all they offer abundant solar energy, which obviously helps with a long-term human presence, but also a relatively benign thermal environment. The equator of the moon varies from about plus 120 Celsius at midday to minus 150 Celsius at midnight. Whereas if you're at a place at the pole that has constant grazing sunlight, it's about minus 50 Celsius and it stays constant. That's much easier to engineer to. Now, any hole near either of the poles is very likely permanently shadowed. It has never seen the sun for perhaps as long as 4 billion years. The only light is scattered light reflected off the inner rim. No direct solar illumination, so they are incredibly cold. Some of the coldest places in the solar system. And they're so cold that they can serve as cold traps for volatiles, particularly water ice. So every time you hear volatiles, essentially predominantly just think water ice, but there could be other useful ices too. So the South Pole is particularly interesting scientifically. The South Pole Aitken Basin is a 2,800 kilometer diameter basin, which one end of the basin rim is at the South Pole, the other edge is at a crater called Aitken, which is why the South Pole Aitken Basin gets its name. Now, when this basin formed over 4 billion years ago, it will have stripped the entire lunar crust that existed at that time. So it will have brought up lunar mantle, which today is either potentially residing on the surface or could be discovered in outcrops associated with later craters. And now, getting a piece of mantle and bringing it back to Earth is sort of a holy grail for geophysicists who want to understand what the internal mechanisms are in terrestrial planets. So now I'm going to talk about the value of lunar polar ice. So ice is a concentrated, easily usable form of hydrogen, which is a very rare element on the moon. It takes 2 orders of magnitude less energy to extract hydrogen from an icy regolith than from a dry regolith. So why is this ice important? Well, if you can crack it into hydrogen and oxygen, you have a source of life support consumables, so you can make the oxygen that the astronauts need to use. Hydrogen and oxygen are reactants for fuel cells that you can then use for the short periods wherein it's dark. Water itself is actually an excellent radiation shielding that you could use for the lunar surface habitats. And hydrogen and oxygen is rocket fuel. It's the same rocket fuel that we used on the space shuttle. So if we can find the ice and extract it, and then convert it into hydrogen and oxygen, it could form the basis of a cislunar transportation system. A key role of the ice is that if we're ever going to explore the solar system with people long term, then we need to learn how to make use of what we find as opposed to take everything from Earth. So essentially we need to learn to live off the land. And learning how to use any ice that we find on the moon is an excellent first step in learning how to live off the land. So what are the sources of lunar polar volatiles? So we now know that the moon essentially has three kinds of water. There's internal water, and this is water that would have existed as part of the formation of the moon. There's external water that is primarily delivered by cometary and asteroid impacts, where some of the water that exists inside these comets and asteroids actually survive, and they make their way to permanently shadowed regions and they are sequestered. Most people assume that all the water would come from comets, but in fact certain kind of asteroids can also contain large amounts of water. And then you have what you would often is referred to as in situ water, and this is water that is made at the moon. One example is that solar wind might interact with the regolith to actually form either hydroxyls or water, and then some of this water also gets sequestered. So a little more about the indigenous lunar water, or the water that's trapped inside the moon. When the Apollo samples were brought back in the 60s and 70s, they were deemed to be 100% dry, i.e. the moon had no internal water. Recent analyses of Apollo 15 green glass pyroclastics, and pyroclastics are the volcanic ash that are made during a fire fountain event, have been found to contain up to 50 parts per million. This implies a much higher magma concentration of water inside the moon. Most water in this magma is lost when the magma is erupted to form the lava flows to form the mare that you see. But the key fact here is the fact the original moon was not completely devolatilized as has previously thought. And one thing that this shows, it shows the value of the lunar samples. They're often referred to as the scientific gift that keeps on giving. It was these new capabilities that exist today that didn't exist at the time of Apollo that are making these new discoveries. And indeed, this year, the ANXA program, which is the Apollo Next Generation Sample Analysis, this is actually going to open a core that hasn't been opened since it was brought back from the moon, so that early career scientists can use modern techniques on this core. I'd like to provide a little bit of history on the search for lunar ice. Now, radar has been used since the 1960s to map planetary surfaces, primarily Mercury and the moon. It's long been recognized that the polar areas near the moon would have the potential to be permanently shadowed and extremely cold. What we didn't know is how pervasive these areas were or how cold they were. Radar analysis of Mercury back in '92 discovered fairly thick ice sheets, and this spurred renewed interest in the possibility of ice in the lunar poles. The first such measurement was conducted using the Clementine bistatic experiment. Clementine was a small satellite that went to the moon in 1992, and it used its communications device essentially as an S-band radar to take measurements at both poles. It conducted 4 such experiments, 2 at each pole. When the radar hits ice at beta 0, essentially pointing straight down, you get an increase in the signal. And they did in fact see this at one place inside the inner rim of Shackleton crater, which is a 20-kilometer impact crater right at the South Pole. Now, this was very complicated viewing geometry, which affected the interpretation of the results. And certainly not all radar scientists believed that the signal that was seen was in fact ice. It was quite a weak signal. They claimed that it was just rocks inside the rim. So this has led to 20 years of controversy about this result, but what isn't controversial is the fact this is certainly the first time that the idea of ice was seriously discussed for the moon. The next key measurement came from a spacecraft called Lunar Prospector. One of the Lunar Prospector instruments was a neutron spectrometer, and what a neutron spectrometer does is it measures the energy of neutrons that are emitted from the lunar surface. When galactic cosmic rays hit the moon, neutrons are ejected at a wide range of energies. Now, the amount of epithermal neutrons, or mid-energy neutrons that you get, is a direct indicator of hydrogen concentrations. So Lunar Prospector measured elevated hydrogen signatures at both poles. That result itself wasn't controversial. Now, the one thing a neutron spectrometer can't do is it can't tell you what chemical form of the hydrogen. It could be plain hydrogen, or it could be hydrogen in water, and it wouldn't make a difference to what the neutron spectrometer would see. It also can't confirm the exact location. A neutron spectrometer is essentially a 4-pi steradian instrument, so its spatial resolution is roughly equal to the altitude of the spacecraft. So the best hydrogen map resolution we got for Lunar Prospector was roughly 30 kilometers, which is too large to be able to determine whether the hydrogen exists inside permanently shadowed craters in a high concentration or was just spread around the lunar poles. The Indian Space Agency in the late 2000s flew a spacecraft to the moon called Chandrayaan-1. NASA flew 2 instruments on Chandrayaan-1. One of them was the Moon Mineralogical Mapper, often referred to as M-cubed. And this was a hyperspectral imager that mapped the moon. And one of the surprise results from M-cubed was spectral evidence for a hydration band at roughly 2.8 microns. This seems to correlate with the higher density for potential water being at higher latitudes as you would expect. The big question is, how would this superficial water be created? It can't exist for long term because the regions where we see it are too hot. So the M-cubed results raise the interesting premise for the first time that the moon might actually have an active water cycle, which is that water is being formed, migrating to the poles, and then being destroyed or sequestered in permanently shadowed regions. One possibility is solar wind reduction of oxides in lunar soil. Another one could be residual water from cometary impacts or outgassed water vapor from the lunar interior. The M-cubed result does represent an important potential source for polar ice. The water ice migrates to the polar cold traps by ballistic hopping, and any that enter would last for a long time. One recent result from the M-cubed data is particularly exciting. A scientist in Hawaii, Dr. Lee, used the signal from inside the permanently shadowed craters with M-cubed to look for water ice. Now, M-cubed, being a hyperspectral imager, requires sunlight to get the data. So you're looking at reflected sunlight. What Lee did is he used the fact that light reflects off the inner rim of the polar craters and you still have a few photons hitting the floor. It's a very low signal. What he did, he essentially summed all the data for a particular portion of the lunar surface that was permanently shadowed, and by summing all the data, even though each individual measurement was very low signal to noise, he built up enough signal to be able to do a measurement. And he, very excitedly, has found evidence for surface frost inside these permanently shadowed craters. I'm going to talk a little bit about a follow-on that NASA will be doing in the near term. In 2016, NASA signed an agreement with the Korean Aerospace Research Institute, KARI, essentially the South Korea Space Agency, to fly a NASA instrument on their lunar orbiter. NASA selected ShadowCam, which will map inside the permanently shadowed regions. It is based on the Lunar Reconnaissance Orbiter narrow-angle camera, but it uses time delay integration to be 800 times more sensitive. So it will actually map, using reflected light as the source, the floors of the impact craters at higher than 2 meters spatial resolution. Its science goals are to look for morphological features that are consistent with a water regolith mixture, and also to look for small impact craters to see whether their ejecta blankets contain bright ice deposits. Another benefit from ShadowCam is that it will be able to map out the boulder distribution inside the craters for the first time. We can use that information to further understand the radar data inside the permanently shadowed craters. In 2009, NASA launched 2 spacecraft to the moon. One was Lunar Reconnaissance Orbiter, that I shall be talking a lot about. The other was LCROSS, which stands for Lunar Crater Observation and Sensing Satellite. Now, the rocket that launched these, the upper stage, which is called a Centaur upper stage, is essentially a fuel tank and an engine that took these 2 spacecraft to the moon. Now, normally what happens with such a mission is that once a Centaur has depleted its fuel, it simply crashes into the moon. Now, what LCROSS did is it was attached to the Centaur, And once the Centaur had finished its burn and LRO had released to go into lunar orbit, the L-Cross spacecraft, with its very small engine, it steered the Centaur so that it missed the Moon, it did 2 large phasing loops around the Earth, and then it crashed into a permanently shadowed crater. Now the Centaur weighed about 2,000 kilograms, and it hit the Moon at about 2.5 kilometers a second. Now this generated at least 200 metric tons of lunar soil that was thrown up into the air. Now, a few minutes before the impact, the L-Cross shepherding spacecraft detached from the Centaur so that it could observe the impact of the Centaur with the Moon, and more importantly, it could use its scientific instruments to look at the ejector cloud that came up. Whilst doing these observations of the ejector cloud, it detected water, up to 6% water, as well as other volatiles. Now this measurement is probably the closest thing that we have right now to ground truth for water at the Moon. Now, one of the Lunar Reconnaissance Orbiter key data sets is the Diviner instrument. Now, Diviner measured surface temperatures for the first time directly at the lunar surface, and it measured it both where it is lit and where it is dark on the Moon. Now, Diviner has mapped places that are lit for part of the time, but are cold enough within 1 meter of the surface that ice can exist. Now, anywhere on the Moon where it's lit gets too warm for ice to survive long term, but the idea of places that are lit some of the time, but you could have ice really close to the surface, are an intriguing possibility and could represent the ideal places for resource extraction on the Moon. Another surprising science result from Diviner is they discovered the coldest location in the entire solar system. It actually exists in a double-shadowed crater on the Moon. This is a shadow inside permanently shadowed, so it's shadowed from even the reflected light from the first crater. And some doubly shadowed places have been found to be as cold as 30 Kelvin, or 30 degrees above absolute zero. This is actually 10 degrees colder than the surface of Pluto. Another key result from both Lunar Reconnaissance Orbiter and Chandrayaan-1 comes from the Mini-RF radars. We flew 2 Mini-RF instruments to the Moon, the first on the Indian Chandrayaan-1 mission, and a more advanced model on Lunar Reconnaissance Orbiter. With Mini-RF, we broadcast a right circular polarized signal, and when this bounces off a typical dry Moon, you get a left polarized signal back. However, if you bounce off ice, or if ice is encountered below the surface, then actually you get the same sense, or you get right circular polarized back instead. This allows you to calculate something called the circular polarization ratio. So essentially, any buried ice, you get a high CPR back with the radar. Now, unfortunately, you can also get high CPR from a rocky terrain, because essentially the radar bounces off the surface and then bounces off the rock and then comes back to the spacecraft. Now, typical lunar craters that have rough ejector blankets have high CPR outside the crater in those ejector blankets that are full of rocks. What we found at the poles is that there are many craters that only exist at the poles where they only have high CPR inside the craters. Now, this could be ice or it could be roughness, but there are a group of scientists who certainly believe that ice plays a role in this signal, because geologically it's very unusual that you would only have high CPR inside the crater and not outside if it was due to roughness. So let's summarize where we think we are with water. Data from LRO, L-Cross, Chandrayaan-1 and other missions have confirmed patchy and/or buried distribution of volatiles, including water. They very likely have different reservoirs. I mentioned there are 3 kinds of water. There's the internal water that was formed when the Moon formed, there's external water that has been delivered to the Moon, and there's in situ water that has been made at the Moon. All 3 of those likely have a different water cycle, and what we're seeing in these enigmatic data sets is the interaction of all 3 of these water cycles. There are 3 groups that are interested in volatiles. You have scientists who care about the science that you learn from studying the volatiles. You have people interested in human exploration who are interested in using the volatiles to turn it into rocket fuel, turn it into oxygen, to help explore. And there's a commercial group who are interested, is there a market there in their volatiles? What's particularly useful for volatiles is the fact that most of the measurements that all three groups want to take are the same measurements. They all care about composition, abundance, what are the regolith properties, what is the lateral distribution, what is the vertical distribution, what is the renewability of, and what is the age of these resources. So volatiles have a multitude of value to all three of these communities. So I'd like to stress the scientific value in the volatiles, and that the lunar polar volatile prospecting has huge scientific benefit as well as exploration benefit. The US uses community-produced documents to drive the science that we try and achieve. The two that you will often hear are the decadal surveys that are made every 10 years, and a document called the Scientific Context for Exploring the Moon, or the SCEM document. Volatiles appear very prominently in both of those community-produced documents. On the human spaceflight side, we have something called strategic knowledge gaps. These are gaps in information which, if we can fill, allow systems to be designed smarter. A good example dating back to Apollo is the lunar footpad for the Apollo landers is actually much larger than it was needed. And that was because we didn't know what lunar regolith was like, and there were some people who thought it would have the bearing strength of talcum powder, and there was a concern that when the landers landed, they would actually sink without a trace below several meters of this fluffy powder. Now, once we sent the robotic landers and we landed with humans, we understood more what the regolith was like, and with hindsight, we could have designed a footpad that was much smaller. A smaller footpad would have had less mass, and obviously less mass is what you go for when you're designing a lander.
Well, we were very worried about our first steps on the moon because some experts had predicted just shortly before launch that we would sink into the surface and wouldn't be able to hold our weight at all, and we'd just disappear into the dust. And of course, we were really pleased to find out that they were wrong.
So that's an example of an SKG from the 60s. We have current SKGs. Many of them are related to enabling long-term human presence, and many of them can be solved by measuring what is the lateral and vertical distribution of the water at the moon. So in fact, lunar polar volatile prospecting addresses the highest priority, both polar science and exploration goals. We are currently working on a rover called VIPER, which stands for Volatile Investigating Polar Exploration Rover, to make the first measurements at one of the poles. It is designed to traverse tens of kilometers so we can measure volatiles over a long length scale. It will provide feed-forward information to follow-on surface missions, and also help us to produce resource maps and through extrapolation with orbital datasets to both poles. It will carry a neutron spectrometer similar to the one that flew on Lunar Prospector, so it will immediately be able to determine whether we have buried enhanced hydrogen. It will then use a drill to drill down up to 1 meter in depth, and then use a near-infrared spectrometer and mass spectrometer to look at and characterize any volatiles that come up with the drill. Now, whilst ice is a major resource, the poles are not good for exploration just because of the ice. Ice is not a requirement for the poles to be a good place to go. The poles are the right place to go for human exploration because of the unique lighting condition. Light is an extremely valuable resource too. And large amounts of lighting is enabling from a human exploration sense because it represents, first of all, the fact it's light, that the crew can go outside and operate. It also means you can have abundant solar energy. And finally, it represents a fairly benign thermal environment for which you have to design your systems to survive long term. So now I'm going to give you some background on what we know about the lighting in the polar regions. The first key information for the lighting, and in fact the first quantitative illumination maps, came from the Clementine mission. It used this camera to map the lunar poles for the first time. What we found is the fact that nowhere appeared to be lit constantly. Remember, because we were looking at the South Pole in winter, theoretically there should be an Antarctic circle at 88.5 degrees for which it is dark inside. We certainly didn't see that. We saw lots of places that were lit very close to the pole in winter. We found 3 places that were lit for more than 70% of a day in winter. And also 2 of those places collectively were lit more than 98% of the time. By that I mean that at least one of those places was receiving sunlight. So if you could put solar arrays at both those sites, then you could have almost constant electricity. For the North Pole, where the data were taken in summer, we did find several places on the rim of Peary crater, which is a 78-kilometer diameter crater near the North Pole, that were constantly illuminated for an entire summer day. Now with those data sets, we couldn't say they were lit all year, but certainly that was an exciting result because it laid the groundwork for the idea that places might exist that are lit for large portions of the year. Now for both the South and North Pole, these regions that receive a lot of sunlight are in close proximity with permanently shadowed regions that I previously mentioned could contain ice. So what you see here is a simulation movie now using each frame of the movie is a simulation that was made using the best lunar topography that we had and simply moving the sun equivalent to every 2 hours in time. And the simulation actually runs for an entire year. The regions in red that you see are the regions that we map out as permanently shadowed. And we can use movies like this, and more importantly, the frames, detailed analysis of the frames that make up, or the simulations that make up the movie, to really do a deep dive into what the illumination conditions are at both polar regions. So we can now map out all key illumination parameters. Some of the key ones are we can locate the places that receive the longest periods of constant sunshine around midsummer. And several research groups around the country and the world have done this. And we now know that there are places that are lit for several months at a time based around midsummer. Now these represent excellent locations for static landers for which you want a long duration mission and you're relying on solar power. Another key parameter is what are the locations that receive the shortest night at midwinter. And again, research teams have found places that are, even at midwinter, their longest period of darkness is a handful of days. It's not the typical 14 days that you get at the equator. And these places are particularly exciting for very long-term operations, because if you can survive that single period of maximum shadow, you can survive essentially forever. You can also do things with simulations like explore the value of a mast. You can explore the value of putting your solar arrays different heights above the surface and seeing how much that increases the time that you see the sun and can generate electricity. And indeed, people who've studied this have found that a moderate mast of a handful of meters does help, but that in order to get 100% sunlight, that's not feasible with a mast. You would need a mast kilometers high. Another key fact for the poles is the fact that the Earth actually gets higher in the sky than the sun does, whereas the sun only gets 1.5 degrees above the nominal horizon. The Earth can actually get about 6 degrees above, and that's due to the inclination of the orbit of the moon around the Earth. So there are regions at both poles that are permanently shadowed, but you can still see the Earth. And these are particularly exciting in the near term, where we want to explore permanently shadowed regions, but we need to have direct-to-Earth communications in order to be able to do so. So what you see here is an image from the Japanese Kaguya spacecraft. And the reason I show this is the places that are labeled A, B, C, D. These were the 4 places that we discovered with Clementine that received the most sunlight at the South Pole. And future analyses with LRO data by several teams has confirmed that these are the places that received the most light. And what I find interesting in this image is when you try and conceive of what are these peaks of enhanced lighting like, you have the idea that you might have like the Rocky Mountains located at these locations, and that's what you need in order to get lots of lighting. But what you can see here is the fact that there's nothing special about these 4 locations. It's incredibly subtle variations in topography that are having large effects on the amount of sunlight that these places receive. I'm going to change topics slightly now and talk about the fact that the ability to have abundant solar energy at the lunar poles might actually allow us to do a different kind of resource extraction before we get to the point where we're extracting buried water ice. It's possible, using different mechanisms, to take dry lunar regolith and convert it to useful products. Hydrogen reduction of regolith essentially passes hydrogen over heated regolith, which contains iron oxide, and this forms iron and water, and then you can crack the water into hydrogen and oxygen. Carbothermal reduction of regolith, you actually have to heat the regolith all the way up to 1600 degrees Celsius to melt it. You then react it to methane, which then forms carbon monoxide, which can be converted to methane and water. And again, you can crack the water. Another technique being considered by the resource utilization community is molten electrolysis of regolith, where you actually, again, you melt the regolith, but this time you put in special electrodes, and that is used to extract oxygen from the molten mixture. So I want to touch upon the fact that the moon is a really big place. The moon has the surface area of Africa. Scientifically and for exploration, we really want global access. I would stress that I think the best way of getting global access is to have a sustained presence and then build your capability. The resources, both water ice and lighting, that you get at the poles, I would argue gives us the opportunity for that sustained presence. Perhaps the best analogy on Earth is the McMurdo field station in Antarctica. McMurdo is the main US base, and it's located on an island just outside the main continent. There are about 1,000 people work there during the summer, and about 300 winter over, keeping the station running. The vast majority of science exploration done on the Antarctic plateau goes through McMurdo. And this is because the existence of McMurdo drastically lowers the logistics that you need in order to be able to explore Antarctica. Essentially, you have to get yourself to McMurdo, and then you can use the transportation, both the planes and helicopters, to take you into Antarctica, also the skidoos that you typically use for driving around, and the tents and all the other materiel that they have in McMurdo. If you didn't have McMurdo, you probably would get almost no scientific exploration of Antarctica, because you would have to go from either South America or New Zealand straight into where you needed to go. So just like the infrastructure of McMurdo enables scientific exploration of the entire Antarctic plateau, sustained human presence at one of the lunar poles can offer the same opportunity for scientific exploration of the whole moon. Initially, early explorers to one of the poles are very likely to explore just the immediate surroundings, using tools like unpressurized rovers to drive around. Eventually, pressurized rovers will allow them to go further. As we build up more capability and infrastructure at one of the poles, I think it's feasible to think about you may end up with hopping with small landers that can hop increased distances from the main field station at one of the poles. And this eventually leads to global access. If we can extract the water to make fuel, then some portions of this lunar transportation system can use fuel that is generated at the moon. So we truly will have begun at that point to live off the land. The poles represent the best place to go for humanity to expand out of low Earth orbit and into the solar system. Essentially, the lunar poles can be our McMurdo into the solar system.